Hello! In this video, we are going to prove the following corollary of the triangle inequality. If a1, a2, an are real numbers, then the absolute value of the sum is less than or equal to the sum of the absolute values. So, in proving this, we're going to use mathematical induction. Right, so let's start with the base case. Now in the base case, we're trying to prove that the corollary is true in the case where n is equal to 1. That is, we're trying to prove if a1 is a real number, then the absolute value of the sum from I equals 1 to 1 of ai is less than or equal to the sum from I equals 1 to 1 of absolute value of ai. Okay, so to start out, let's give ourselves an arbitrary real number a1. And our goal is to prove this inequality in the case where n is equal to 1. Let's start out by writing the left-hand side. Now, the sum from I equals 1 to 1 of ai is just a1. Right, because when the lower and upper bounds of a sum are the same, all you do is you take the everywhere you see an I and replace it with that lower and upper bound, 1. But really, the absolute value of a1 is the same thing as the sum from I equals 1 to 1 of absolute value of ai. And the reason why is because of the same thing. Because whenever we have the lower and upper bound of a sum the same, all we do is we take wherever we see an I and replace it with that lower and upper bound, 1. And that's it. We see that this is less than or equal to this, which means we have proven that this is true in the case where n is equal to 1. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer n, and we assume that for this arbitrary positive integer n, that this statement is true. Right, so we give ourselves an arbitrary positive integer n, and we're assuming that this arbitrary positive integer n satisfies the statement. The whole goal of the induction step now is to prove that the statement is also satisfied for n plus 1. And to do that, we're trying to prove if these are real numbers, then this is true. So let's suppose that a1, a2, an plus 1 are real numbers. And with these n plus 1 real numbers, we want to prove that this inequality is true for n plus 1. And to do that, let's start out by writing the left-hand side. Now, if you recall, one of the properties of summations is if the upper bound is strictly bigger than the lower bound, then we can pull away the n plus 1th term from the sum. That is, we can rewrite this sum as the sum from I equals 1 to n of ai plus an plus 1. Right, so we can all agree that this sum is precisely equal to what we have here. But now, we can apply the triangle inequality. From the triangle inequality, the absolute value of this is really just going to be less than or equal to the absolute value of this plus the absolute value of this. But now, we would like to say that this term is less than or equal to this. And we can do that because a1, a2, an is a list of real numbers. So this must be true. Therefore, this term must be less than or equal to this by our induction hypothesis. And now notice, we have the sum from I equals 1 to n of absolute value of ai, but really, the absolute value of an plus 1 is really the n plus 1th term of absolute value of ai. So we can essentially take this term and add it on to the sum that we have here. So really, this entire thing is just the sum from I equals 1 to n plus 1 of absolute value of ai. And notice what we've done here through this chain of equalities and inequalities. we have proven that this is less than or equal to this, which means we've proven that this is true, where instead of n, we have n plus 1. And that was the whole goal of the induction step. So this completes the induction step. Because we've proven the base case in the induction step, this closes the induction, which means we have proven that this statement is true for all positive integers n. So we've proven the corollary. So this completes the proof. And so yeah, that's pretty much it for this video.